Welcome back, everybody. This is our sixth session in JEE mains previous year questions for chapter Magnetism and Matter of class 12th. Before this video, we have made 5 videos in this series, and all of those videos are available on our channel's playlist section. We have also started similar series for NEET previous years. So, if some of your friends are preparing for that, then you can guide them through those videos. And if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. In the previous one, we completed around up to around 35, I think. We completed this one. Now let's start with the question number 36. The materials to be suitable for making electromagnets should have. Now we want to make electromagnets, and depending upon the application of the electromagnets, things can vary. So normally electromagnets are used in place of actual magnets. But we know that to create an actual magnet of very high strength, space is a big constraint. In case of electromagnet, a magnet with high pole strength can be easily made with a very small size. So if we are replacing actual magnet with an electromagnet, then it is required for actual magnet to have its we can say to retain its magnetic property over the time. And for electromagnet to retain its property over the time, it needs to have high retentivity and high corrosivity. So in that regard, option C will be the right answer. But if we are using electromagnet in the transformer course, the electromagnet is kept in the cycles of magnetization and demagnetization. Here electromagnets goes through cycles of magnetization and demagnetization. And why this happens? Because in an electromagnet, AC flows through the circuit. So in the positive half of the cycle, electromagnets gets magnetized. In the negative half of the cycle, it gets demagnetized. So in this scenario, the area of the hysteresis loop, the hysteresis loops look like this. The area of hysteresis loop decides the amount of energy loop in energy loss through the whole cycle. And in case of transformers, we need this energy loss to be minimum. And in that regard, option B will be the right answer, that we need low retentivity and low corrosivity. So here it is not specifically mentioned that whether this electromagnet is going to replace actual magnet or it will work as a transformer core. So depending upon the use, normally high retentivity and high corrosivity is the general answer. Now let's move to next question. A thin rectangular magnet suspended freely has a period of oscillation equal to T, now broken into two equal halves, each half each having half of the original length. One piece is made to oscillate freely in the same field. The period of oscillation we have to find out. Now to solve this, let's suppose we have a magnet. Initially, we had a magnet with pole strength small m and length small l. Now we broke it into two pieces. As after breaking, pole strength does not change, so pole strength say m, length becomes l by 2, and there is second part with pole strength m and length L by 2. Now dipole moment, magnetic dipole moment of this magnet is ml. For this magnet it is ml by 2, and for this magnet it is ml by 2. Now we also needed another term, moment of inertia. Why? Because oscillating magnet, for time period for a oscillating magnet in a moment magnetic field is given by T is equal to 2 pi under root I m b, where m, this m is the magnetic dipole moment, that is small ml, and I is the moment of inertia. So we also have to calculate the moment of inertia. And uh, it is not mentioned that about freely suspended. So we assume that these magnets are oscillating around their center point. So if they are oscillating around their center point, then their moment of inertia, for this moment of inertia will be ml square by 12, where m is mass and we have used multiple m's here. So let's write it small m. For okay, let's write it p. Magnetic dipole moment we are writing with the help of p. We are writing it as p. This is magnetic dipole moment, and for mass we will use capital M. So for this, if its mass is capital M and its pole strength is small m, there is difference between small m and capital M, and length is L. So moment of inertia of this magnet around its center, perpendicular to its center point, is ml square by 12. Now we have to choose one of these because only half. Now in the second case, one half is oscillating. So I dash for this one will be, now as a length reduced to half, mass also reduced to half, m. Now length is L by 2 divided by 12. So it will be ml square by 2 into 4, 8 by 12. So ml square by 8 into 12. That's a new moment of inertia. Now in this expression 2 pi is same for both of these. Magnetic field is same. So let's compare the other values. We can say T by T dash, or we have to find out T dash by T. So T dash by T will be I dash P dash B will be same divided by I P B. Now B is same, I dash is capital M L square by 8 into 12, and I is M L square by 12. Now P is the magnetic dipole moment of the original magnet, that is small m into L, and P dash magnetic moment of the half of the magnet, that is ml by 2. So ml by 2. ml get cancelled, ml square get cancelled, 12 gets cancelled. So we are left with 2 by 8 or 1 by 4. Under root 1 by 4 will be 1 by 2. So T dash by T will be half. Option B will be the right answer. Let's move to next one. Curie temperature is the temperature above which, so it is a temperature above which a ferromagnetic materials becomes into diamagnetic material. So ferro to para, para to dia, ferro to dia. Option C will be the right answer here. Let's move to next one. A ring is hung on a nail, can oscillate without slipping or sliding in its plane with time period in its plane with time period t1, and back and forth in the direction perpendicular to plane with time period t2. So we have to find out the ratio of both of these. So let's draw a ring first. Suppose this is our ring, and it can oscillate in the two ways. One is along this axis. This axis is perpendicular to its diameter. This axis is parallel to its diameter. Suppose this is its diameter. So this axis is parallel to this its diameter. And one more axis that is perpendicular to its diameter, something like this. So let's name these axes. So suppose center is O and this point is O dash. So X, O, X dash and Y, Y dash. Now, it is not mentioned in the question that we have a magnetic field or not, and also whether some current is flowing through this ring or not. Now, in both of these cases, we assume that as this is a chapter of magnetism and it is oscillating, so there will be some magnetic field, some torque, and there will be some current in this ring, so that it is acting as a magnetic dipole. And in both of these cases, neither the dipole moment is changing, neither the field is changing, just moment of inertia is changing about the different axes. We know that time period for an oscillating magnetic dipole inside a magnetic field is given by I, moment of inertia, divided by magnetic dipole moment into B, where B is the magnetic field. So magnetic field is constant and M is constant because M is N times I times area. M is N times I times A, where N is the number of turns, I is the current, and A is the area. So whatever the axis we choose, value of M is going to stay the same, value of magnetic field is going to stay the same. So we can say T1 by T2, their ratio will be dependent just on ratio of moment of inertias. So this is our in plane and without slipping or sliding in plane. So that's our T1. Oh, sorry, axis 1, and perpendicular to plane, this is our axis 2. So let's find out moment of inertia around this axis. So I1. Now we know this is a ring. Suppose radius is r, and if its radius is r, then its moment of inertia about the its diameter, this diameter, we can say diameter pp dash. Its diameter pp dash will be half of the mr square. So I1 will be moment of inertia about diameter pp dash plus mass times the distance between xox and pp dash, because xox axis and pp dash axis both are parallel. So mass times the r square. So it will be half mr square plus mr square, that will be 3 by 2 mr square. Now going for the second. Now this second axis is perpendicular to the plane of the ring. So similarly, we can also draw an axis that is perpendicular to the plane of the ring and going to the center of the ring. Now around this, let call it Q dash. So I2 will be moment of inertia, as Q dash and Y dash are parallel. So it will be I Q dash plus mr square. And we know that for an axis which is passing through perpendicular to the ring, Moment of inertia about that axis is mr square. So mr square plus mr square is equal to 2mr square. So we have the moment of inertia. If we put values here, I1 is 3 by 2 mr square divided by 2 mr square. So mr square get cancelled. We are left with 3 under root 3 by 4, or that will be root 3 by 2. So, and if we see here, we are getting answer, but in the our relation is inverse. So let me check it again. In its plane with time period t1 and back and forth in the direction perpendicular to its plane. Okay, so it is oscillating about x o x with a ring oscillating such that it is oscillating in the z axis. So it is coming out of the screen and going into the screen. So that will be our I1. So I1 is actually here that we saw, that is I2, and that is I1. So this will be T2 by T1, or we can simply say, okay, T2 by T1, and here we will have I2 and I1. Now it will be okay. So let's move to next one. A magnetic compass needle oscillates 30 times per minute in a plane where dip is 45 degree and 40 times per minute where dip is 30 degree. So due to dip, the value of magnetic field is changing. If B1, B2 are respectively the total magnetic field due to Earth at the two places, then the ratio of B1 and B2 is. Now we know in case of magnetic field, the angle of dip is with the vertical direction. So suppose this is the original value of the field. Suppose that is B1. So this is horizontal direction and this is vertical direction. So this is the angle of dip. Oh, sorry, not. This is the angle of dip. So here angle of dip is mentioned in two cases. So suppose that is theta. So horizontal field will be, if this is B, the horizontal field will be B cos theta. Now oscillations are mentioned. So formula for oscillation, time period for oscillation is 2 pi under root I dot mb. And as magnetic needle is not changing, neither its axis is changing. So I is constant here, magnetic dipole moment is constant here, so only depends on the magnetic field. So we can say T1 by T2 is equal to B1 by B2, and B1, this B1 is the horizontal component of the field, so it will be here B1 cos theta, and for second it will be B2 cos theta. Now coming to the time periods, that time period for first or oscillations are 30 times per minute. So in a second, in a minute, it oscillates 30 times. So we can say one oscillation takes 2 seconds for the first case, and for the second case there is 40 oscillation per minute. So one oscillation takes 3 by 2 seconds. So T1 will be 2 and T2 will be 3 by 2 is equal to B1 cos of theta, that is 45 in the first. So cos 45, that is 1 by root 2, and 30 in the second. So cos of 30, that will be root 3 by 2. So squaring both of these sides, we will get 4 square 16 by 9 is equal to B1, B2, we have 2 root 2 root 3 here, and ratio of B1 B2 will be 8. So 8 root 2 into root 3 divided by 9. Sorry, again we made a mistake that it time period is inversely proportional to magnetic field, so it will be B2 by B1. Or we can say this will be here T2 by T1. That will be easier to correct. So this side will be corrected, and let's this whole to be changed. So it will be T2, that is 3 by 2 divided by T1, that is 2. So now squaring both of these, so it will be 9 by 16 is equal to B1, B2, 1 by root 2, 1 by root 3 and 2 here. So B1 by B2 is equal to 9 root 2 root 3 divided by 32. And solving this, we get zero point 0.7. So option B will be the right answer. Keep in mind this, we made a mistake here previously. As time is inversely proportional to the field, we took it directly proportional. Now let's move to the next question. A hoop and solid cylinder of same mass and radius are made of permanent magnetic material with their magnetic moment parallel to respective axis, but magnetic moment of hoop is twice that of solid cylinder. So magnetic moment of hoop is twice the magnetic moment of cylinder. They are placed in uniform field such that manner that magnetic moments make small angle with the field. If the oscillation period of hoop and cylinder are TH, TC respectively, then we have to find the relation between them. So first of all, let's discuss about what is hoop. So hoop is a ring-like structure. So moment of inertia of hoop, which will be needed here, will be equal to mr square. And this cylinder is solid cylinder, so it will behave like a disk, we can say, and moment of inertia of cylinder, if it is solid, that is half mr square. So let's now compare their time periods. Now time period in a field is 2 pi under root I m dot b. As field is same for both of these, only moment of inertia and magnetic moments are changing. So we can say T hoop by T cylinder will be equal to under root moment of inertia of hoop divided by magnetic moment of hoop, moment of inertia of cylinder divided by the magnetic moment of the cylinder. And now we know mc by mh. From this, half is equal to mc by mh. So this will be half. IH is mr square and IC is half mr square. So half mr square. Mr cancel, 2 cancel. So we are getting 1, means TH is equal to TC. Option A will be the right answer here. Let's move to next one. A magnetic needle of magnetic moment, this moment of inertia is this performing SHM in magnetic field of this one, time taken for 10 complete oscillations. So what we will have to calculate, we have to calculate first the time period, then multiply it by 10. So time period will be 2 pi under root I m dot p. So 2 pi I is 7.5 10 raised to power minus 6. M is 6, 7 into 10 raised to power minus 2. B is 1 into 10 raised to power minus 2. And solving all of this, we can say, not we can say, let's solve this whole. So here we will have This is 2 pi into 75 by 67 and 10 raised to power minus 2. Now 10 raised to power minus 2 will be outside, so it will be 2 pi 10 raised to power minus 1. So 10 raised to power 2 outside will become 10 raised to power minus 1. So 2 pi by 10 into 75 by 67. Now this value will give us will give us something like 1.001, and under root of that will be also around 1. So we ignore it or approximate it to 2 pi by 10, and we have to find time period for 10 oscillations for, and this is for one oscillation. For 10 oscillation it will be 10t, so 2 pi by 10 into 10, that will be 2 pi, and 2 pi is 6.28 seconds, so that nearestly matches to 6.65. That will be the our answer. So with this we end this video here, and this chapter is also completed. Again, if you have any doubts or suggestion, put them in comment section. I will try to resolve or answer or implement. If you find this video useful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, again, thanks for watching, and we will meet in next video.